share my screen. Yeah, so am I audible and my screen is visible?
Yes, sir. Yes, sir.
Okay, good. So today we will be going to discuss about a new kind of a model which essentially can help in every sort of learning that we did in this semester. So though that function you are already introduced in the last class is called radial basis function, or in short we call it as RBFs. So basically the goal of this function is that still now whatever you have seen, you try to build an hypothesis from training examples. So every example in the training plays a part on it, whether you do stochastic gradient, batch gradient, or minimize directly in linear regression. What happens is that every example plays a part in order to build a hypothesis. That's natural. Now, what if for a point, the nearby points play more part to shaping or to classifying the level of that point rather than the farthest point? In other words, if you look at this curve, suppose I have a point here, X. Now see all the points that are far away, here is the influence of the other points in getting the level of this. So that's a very natural model of assumption, because obviously which we classify usually but an unknown point, the nearby ones actually influences it more than the further ones. So we want to build a model where not only the point and the other points class matters, but also the distance of these points to any other point will be of our interest. For any n that you are given in the training set from 1 to capital N number of points, and we do a square distance formula. So this will play a role in shaping the level of this point or in defining the model. And I would like to make sure the smaller distance contributes much. So now the contribution is a parameterized contribution, and since, as you can see, this curve of contribution is something called Gaussian, so obviously it is nothing but an exponential function of this, the influence of any other points with this x. So what if I declare my hypothesis with respect to these functions? So first of all, let us try to understand that why this function is called radial basis function. First of all, it is radial due to this fact. Why? Because you can see I can build around it a particular radius, and all of the points that belong to this within this radius or and the boundary of this radius has a similar influence. It's a Gaussian curve, 3 dimension. So that's why this relationship makes the function name to be radial. And why it's a basis function? Because this is a Gaussian basis we have. So we took the basis or the base function to be an exponential Gaussian nature. So we call this function as a Bayesian function. So this is the radial part and this is the basis part. So we understood that what model we are trying to learn here. Now we need to figure out that different learning algorithms, how they explore and come up with a solution with respect to this model. So when we say different learning algorithm, it means that my model, let me figure out, let us start with linear regression first. So in linear regression, what we do, you take each of the points, you have this as a function with respect to each of the points, and then for each of the points you try to learn a weight, and in linear regression you sum up that weight, so from n equal to 1 to capital N, all the points. That's your linear regression model. And what is your objective? Your objective is, depending on every training point that you get, ultimately you need to learn this. So let us see that how we can do this. And in fact, to learn this, what we have seen in linear regression, so I will just recapitulate our concepts and try to show that this basis function is very much indeed very much helpful. We try to minimize the error to 0. In order to minimize the error, that means when we try to minimize the error, that this function for every point will be equal to yn. So this is for x1, this is the function that I predict for y1, it should be equal to y1. So the situation is a bit more simple because I have for every point I equal to 1, or rather n equal to 1 to capital N, wn e to the power minus gamma x minus xn square. This should be equal to yn. So this, as I told that this is simple because if you can see there are n equations and there are n unknowns, right? Because this is a sum. If n equal to 1, this is a sum equal to y1, then 2, then 3 up to capital N. So there are n equations and n unknowns. Pretty simple job. What we will do, we will try to solve it using the traditional method that we have seen. So this will be our matrix of radial basis. This will be our matrix of weight, equal to this will be our matrix of outcomes. So if I try to fill this up, this will be e to the power minus gamma x1 minus x1 square, e to the power minus gamma x2 minus x1 square, e to the power minus gamma x3 minus x1 square, and so on. Similarly, in this side, if you move, at the end it will be e to the power minus gamma x1 minus x capital N square. This side, if you move, e to the power minus gamma x2 minus xn capital square, and so on. Here, as you know, this will be w1 up to wn. Here, this will be y1 up to yn. And absolutely, if this becomes an invertible matrix, you immediately can derive the solution here, that my weight will be equal to this inverse y. It's a one-step solution, and often we call it as an exact interpolation. Right? So essentially, you can see that I can model linear regression using this kind of model where my objective model of learning is radial basis function. Agreed? This is straightforward, right? The linear regression principle. Any questions in that?
Sir, excuse me, sir. I think in this part, won't there be overfitting or something like we are exactly matching the?
No, in linear regression, usually we put the weights equal to 0. Now, we just are following the linear regression one-step batch kind of a solution. In linear regression, see, either this is one step or this will be a pseudo inverse that I will come later, right? So,
Okay, sir.
in case of you are right. See, in linear regression, what we do is that we try to minimize the error. And in order to minimize this, one way is that, as you said, we could overfit. The other way is that we could make the differences square and the sum of that to be minimized, right? So according to you, what we will also try to make in order to restrict overfit, we will try to make for each of the i's this sum over I equal to 1 to n. I would like to minimize this, right? Isn't it?
Yes, sir.
So therefore, I mean, if you also try to
Yes, sir.
minimize, see, if you also try to minimize this, ultimately you have this function in n. So you want a wn. To exact order to minimize is that you can tell that every y I should choose a Wn in such a way that every y matches. And now I have n equations and n unknowns. That helps me a lot, because now I can just derive upon exactly what I want in terms of my y. Okay, so that's what we want to go. But you are right that it has a chance of overfitting question arises rather than if we do this one. Good. Now see, there is an unknown parameter that we already not discussed, is this one, gamma. Let us try to see the impact on gamma when we try to do linear regression for and try to interpolate exactly and do a linear regression. So as you can understand, if gamma is large, then what will happen? If gamma is large, then this Gaussian curve will be much more steeper. Did you get it? If gamma is large, then the Gaussian curve will be much more steeper, right? For gamma become large.
Yes, sir.
If gamma is small, it will be much more smoother for small gamma. So let us try to see the impact on linear regression with respect to this small gamma and capital gamma. So what we are doing in linear regression, suppose we have 3 points. So this is the curve for 3 points. Obviously, this point will fit better in this position, because with respect to only this point, this curve suffices, because this is the position and the influence will die down. With respect to this point, this is the peak position. With respect to this point, this is the peak position. Now, finally, when you are trying to learn this, the function of hypothesis, which is this one, this one, then obviously if your gamma becomes small, then you land up in extrapolating in a much smoother way, because this does not kill. All of them sums up with respect to an weight, it sums up and blows up. This does not kill the intermediate points to that much, because you have a smooth or flatter Gaussians. Whereas in this case, when you have a steep Gaussians, so each of them die down immediately after fitting it. So you can see that the final hypothesis you are getting is the blue one. The final hypothesis of the extrapolation is the blue one that you are getting. And you can see there is a steep jump. And here, there is a chance that you are getting more overfit than this one. Agreed?
Yes, sir. Agreed.
Okay. Now, similarly, we saw linear regression. We can apply linear regression to linear classification as well. You have seen all this, but with respect to radial basis function, RBF, we have not seen these factors. So I just am revisiting your existing knowledge. So what does the linear classification problem will look for a model? It will look not the sum, but rather the sign of the same thing. Now, we have the training data in our hand, remember, and the training data is nothing but now plus minus 1, any one of them, x2 plus minus 1, so on up to xn plus minus 1. So all the yns now are either plus 1 or minus 1, because we are doing a classification instead of linear regression. So you know that linear regression algorithm we can reuse in classification. Just what do you do? That let's say this is my sum, and I will try to minimize as per your friend's suggestions rather than directly equally. I will try to minimize my sum minus y square on the d data points that are given to me, provided my y is equal to plus minus 1. Right? The same thing I will do. Instead of taking a value for yn, all yi's I will try to do is plus minus 1. Right? Then finally, when I will minimize this one, my final solution would be nothing but I will take hx equal to sine of s, where s minimizes the error. And by s means s is nothing but a function of all the w's that I am learning. Right? Same thing. I mean, I'm just not doing anything new here. You know how to convert linear regression into linear classification. Instead of taking the output as a value, you can apply the same algorithm, which is my weight will be phi inverse y, where you know that y will take the value plus or minus 1. Nothing else. You will try to equate and take out the value of w, and that will act as an hypothesis like this. Okay. So the conclusion is that radial basis function as a model can be applied to both linear regression as well as linear classification quite easily. Right? And indeed, this is a good model because this has an influence of the nearer points more than the further points. Okay, part 1. Let us move on. What else we have seen in our learning? We have also seen that these are all parameterized because the parameter wn you are trying to learn. We have seen non-parameterized algorithms like nearest neighbors. Let us see whether RBF models nearest neighbors or not. It seems very natural to model nearest neighbor because the further the points are, the less influence, and the nearer the points, the influence is more, obviously qualifies it much nearer to the nearest neighbor kind of algorithms. Remember this one? What is this called?
Voronoi diagram.
Yeah, Voronoi diagram, and each cell is the tessellation of these points. So this is with respect to one nearest neighbor, right? So now we are talking about nearest neighbors, and this is basically one nearest neighbor. So the philosophy goes that every point in a particular tessellation, if I choose any arbitrary point, it will be labeled as plus. Similarly, in any other points in, let's say, in this tessellation, if I choose any arbitrary point, it will be labeled as 30. That's the principle. Now see that in one nearest neighbor, actually your basis function is a little bit different than Gaussian, because here you are assuming a very stringent boundary. So it's just like a function, your basis function will act like a cylinder, because what you are assuming is that within this radius, everywhere I go within this radius, I am equally contributed towards classifying the points. You can see here, though it just interferes with other points, so the radius become truncated in between, but it looks like I have a fixed influence up to a certain point, and then influence drops directly to 0. Agreed?
Yes, sir.
So therefore, here is your basis function for nearest neighbor. And in particular, for one nearest neighbor, the basis function looks like this. Just I am changing the radial, the basis function. Radial becomes same. Instead of Gaussian, I take this. Rather, in case of k nearest neighbor, the Gaussian function matters very much, because now I see that I will try to, what happens in case of k nearest neighbor, I will try to draw within a point, I will try to draw k nearest points in that. What does it mean? That the points further to it may not have any influence on that. So if I say that they do not have any influence, then this basis function again will result, because I am only looking for a fixed radius. After that, it drastically is 0. Or I could also use a Gaussian kind of an influence in terms of finding the nearest neighbor. When we taught this, we have seen that instead of the distance of the function, you can see how the distance or similarity drops with respect to distance, and it may not be abrupt, but it could be a Gaussian. So let us try to see, if it is a Gaussian, then how do we go with our algorithms that we learned for nearest neighbors. So obviously what we have to do for nearest neighbors, we have to choose k centers, right? Where our k is much smaller than n, right? We have to choose k centers, and therefore the k centers, let us call it as mu1, mu2, mu k. So the hypothesis function, if I go for radial basis with a Gaussian one, is basically you are trying to choose RBFs with k centers. So therefore, obviously your k is equal to 1 from capital K. You are trying to find k weights such that this becomes your Gaussian function. So what essentially I am trying to do, I am trying to find k points with which some key points with which I was trying to look for the Gaussian distribution. So, and the Gaussian distributions accordingly drops like that. So what it will make an impact, suppose I get a new point, I can see the distance, how does it drops and all that, and try to classify it there. So here radial basis, if we want to choose k centers, the question comes, we see now the two parameters we need to learn. One is mu k, one is wk. Two parameters we need to learn. So the question comes is that how we choose mu k and how we choose this wk while learning from the set of data points given to us. So you know what is the objective here. The objective here is that I have given data points x1 up to xn, right? I want to cluster them into k classes, s1 to sk. These are my data points, and these are the classes that I wish to do. What will be my objective function with respect to this? I want to minimize, first of all, for every point, the distance with some center k. That I would wish to minimize. For every point, the distance with some center k, this should be minimized for all points within a particular class boundary I have chosen. And this should be minimized with respect to all class boundaries for all the classes, right? This is what I need to choose. So k centers, if I can choose in such a way that the data points that belong to a center, that distance get minimized, and it happens for every one of them, right? Yes or no? Agreed or still in doubt? Hello, am I audible?
Yes.
See, what I did here is that in nearest neighbor problem, here I assume two things. Let me just show the shift of from the nearest neighbor to this problem. In nearest neighbor, I have a basis function which is getting a cylindrical type. For k nearest neighbor, maybe this cylinder width or the radius of this cylinder is bigger. For one nearest neighbor, the radius of the cylinder is small. That's where we end nearest neighbor, right? Now, when I move from nearest neighbor has a resemblance with making clusters. The nearest neighbor has a resemblance with making clusters. There you see, I only give you points, but not their labels. Agreed? There I need to only know k centers of them. Therefore, I need to cluster them into k classes such that inter-cluster distance is minimized among all points. That's what I only framed in these equations.
Yes.
So gradually you see I am also using this kind of Gaussian and nearest neighbor influences in doing k-means clustering, which I will just explain once again. If you remember what we do in k-means clustering algorithm, that we choose k centers and gradually we refine it. So the main challenge of this objective function is NP hard to attain. Computationally, it is NP hard. There is a class of problems which is NP hard. That means deterministic polynomial time solutions cannot be possible. Okay, it is deterministic polynomial time solutions is not known. It is non-deterministic polynomial time hard. So which means that I could have to do some kind of an iterative approach, and my iterative approach should first try to fix this mu case, this ones, and then try to go for choosing this w case. That's what we did in all our previous lectures, which is, and you do not know the name of the algorithm. I didn't mention in k-means clustering. It's a Lloyd's algorithm. What does Lloyd's algorithm do? You start with an arbitrary k points, remember, and try to form a cluster with those arbitrary k points. So
Yes, yes.
your arbitrary k points in each iteration gets updated by the clusters that you get into that xn belongs to sk, and you go on doing the mean of those, right? This is the updation of your whatever you know as the updation of mean in each iteration is this one, right? So you start with any arbitrary k number of points. All the other points you try to make a cluster with all the nearby points. Then adjust the mean a little, adjust the mean. So adjustment of the mean means all the points that are participating in the cluster divided by the cluster size is your mean. That's how you update. This is your update rule. And then once you update, your newly formed cluster rule will be all those points you put into that cluster such that the distance with respect to the mean that you have chosen, new mean that you have chosen, is less than all other means that have. Agreed? These are your two rules that by which you do k-means clustering again and again. You go on repeating these two steps. Yes or no?
Yes, yes.
Arbitrary select point, choose a nearby boundary, update mu k. Once you update mu k with respect to that, those who are nearer than any other boundary, this will be mu k. Any other boundary, any other mu k's are put into one cluster sk. Go again, update your mean, do this. Update, do this. Finally, you convert somewhere. Now, this method will obviously convert because your point set is finite, right? Just listen to this very carefully. Why this method will converge? Because your number of points are finite, number one. And secondly, since the point is finite, therefore the number of average mean totally possible is also finite. So the switching between the means can be arbitrarily many, but it will not be infinite since your number of points is finite. Right? But however, you will go down to a local minima rather than a global minima due to this fact of NP hardness inherent in this problem. Right? So you can easily see how the Gaussian thing also comes here as a model to cluster or to do unsupervised learning as well. Questions? Any questions? Shall I proceed?
Yes, sir.
Now see, there is an interesting ramification with respect to the support vectors of with this. Now just let me blow up this figure, then I will shrink again to make you more amenable what is happening. Suppose I am given with this levels, right? I am given with this levels. Now, what you do in support vector, you may transform somewhere, invoke a kernel. Finally, you want to do this line. As you can see, your support vectors are one are this, one is just here, one is just here, one is just here, and obviously in the blue side, one is here, 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 and here. With respect to this, you draw your support vector. With respect to this margin, you draw your support vector line. Now forget about the levels. When you do unsupervised thing, you do not have any knowledge about the plus and the crosses, right? When you do unsupervised things and try to find out centers, then effectively you are trying to figure out, okay, this center finally converges due to this class. This center finally converges maybe due to this class. This center finally converges maybe due to this class. This center may be due to this class. This center is somewhat this. This center is somewhat this. This center maybe is like this. This center may be of like this, and this center may be of this part. Right? In this way, you make the center. Maybe these points are also included in this center. Right? Yes or no?
Yes, sir.
Now suppose you see that if you are not given the levels, you come up with these kind of things. Obviously, with respect to the correct, so even if you are not given the levels, if they have a level, suppose I give you the weights and size of a coin, I need to cluster it into it's a 1 rupee or a 2 rupee or a 5 rupee coin. So you do not know the level, but inherently the problem data points has the level. Now you can see there are only in case of center forming or cluster forming, there will be some points which can go either way. I mean, the level of which can go either way, either +1 or -1. But most of those points, when you form a cluster, each cluster is somewhat of uniform level, right? This may be in the -1, this may be in the -1 side. So there is a certain association between these two things in a form that even if you do not know what the cluster is, if your boundary is a little bit if your margin is more in getting support vectors, then obviously the clusters that you will form will be disjoint in terms of the levels. Agreed with this claim? Yes or no? Suppose my margin is wide. I do not have very close boundary points in the margin. The wider the margin, the cluster form will be more tuned towards forming uniform level clusters, not like this one. Yes or no?
Yes, sir.
Sir, not here.
Okay. So what I was trying to say here is that, see, suppose you have points with levels. You know how to make support vectors, and you have a margin and you can draw the separation. Right? Now, suppose you do not have the level of the point. Therefore, you want to go for unsupervised clustering of the points. Now, there will be some centers around which the points may behave as if your level is given, it will be either +1 or -1 in both. But if I have a wider margin in terms of support vectors, most likely, suppose this is my margin, suppose my points are here. I have a wider margin like this. So obviously your clusters will be formed with respect to center,
Yes.
here, center. So you can see that either if I give the level, since this side, if I assume +1 and this side of the margin, I assume -1. So obviously your cluster will also indicate that level uniformly, that this is -1 cluster and these are +1 cluster. Though you do not know -1s or +1s. Right?
Yes, sir. I got it now. I got
Yeah.
it now. Yes, sir.
So therefore, when we choose μk, and finally our job is to choose wk, what we will do is that we will try to solve this equation, k equal to 1 to capital K, wk e to the power the same radial basis Gaussian one, x n minus mu k square. Now you see that if this cluster separation is wider, if it mimics whatever be my point at nth instance, I will try to make it almost mapping to that. So if my cluster point is in this side, I will try to make it +1. If the cluster comes in this side, I will try to make it -1. But this is almost due to this scenario. Not always it is the case. So that's why I have an almost. So now you see, if it were equal to, then I have k unknowns, n equations. Because for all n points, I have n equations, n different equations. That is for all n. Each of n, I have one equation like this. So if it is equal, then it is not bothering. But if it is almost equal, then what we do again, we will try to use that this is my phi matrix, that is the matrix of this one. This is my W matrix, and this is almost equal Y. And you know how to solve it now. We will do this form that if phi transpose phi is invertible, then obviously my W matrix, even if you can use the gradient descent, which is the pseudo inverse, right? This makes sense because you have already learned this. Since these are not equal, I will try to minimize the error by gradient descent. I can do a batch gradient descent because I have the whole matrix in my hand now. And similarly, I can go on doing this and apply our generic, that our knowledge of pseudo inverse, and get the weights W. Okay, the ramifications of RBF towards support vectors as well as clustering is understood.
Yes, sir.
Next, let us try to look the RBF as a network. So why I want to look the RBF as a network? Suppose this is your X. At the next level, you have your basis function acting over X. So this is one basis function which acts over S with the distance of X minus, or rather mu1. This, I can say, another basis function which acts with the distance mu2. Similarly, I go on, this which acts with S with the distance of X with mu k. Right? So each of them is kind of, this function is nothing but e to the power minus gamma, whatever comes in here. This with respect to this. This is my transformation of this layer. Now, second layer, I have weights W1, W2 up to Wk. And finally, I compose the weights in terms of a sum unit, passes out with my hypothesis. Agreed? This was our form. Yes or no? That's what we did.
Yes, sir. Agree.
This is RBF network we are talking about. Now, when we talk about this kind of a network, let us try to take a resemblance with our neural network. Let's say two-layer neural network, X there is a nonlinear transformation theta. There is a nonlinear transformation theta. All of them comes with the weights, and finally I have a composition layer. So just I am indicating with a different arrow in the composition. So here this is my W1, here this is my W2, here this is my Wk. And here, as you can understand, it is nothing but Wt1 into X get sigmoid transformed, then added up. This is WT2 into X. X is a vector, remember, X is a vector. This is WKT into X. This is our traditional neural network. Now let us try to see that, first let us try to see the similarity. These two layers, this layer and this layer, both are nonlinear, right? Now, you can view this RBF in a two-layer network. You can also view a two-layer neural network like this. You can see that at each layer through back propagation, you update the values of weight at each layer. Here, it's a difficult function, so back propagation might not work in that sense. So what we do, we go on iteratively fixing this and then fixing this. So kind of we iteratively update and fix this, but all with minimizing the error. So both of them tries to minimize the error finally. And also you can think of this as, if you go by a support vector machine, so you can think that support vector machine, you can also design it as a two-layer neural network format. In the first layer of the support vectors, you get the support vector, and in the second layer, you compose the support vectors to get the margin and the final separation or discriminant. So effectively, this has some resemblance with neural network as well. Okay, so just I am trying to relate all this together in every of the learning aspect that we learned so far. So here the resemblance is due to the fact that we are assuming nearer points to be acting more in this, further points will be acting less. Here the resemblance is nothing but like this, where there is nearer and farther is not makes a sense. Beyond the threshold, everything has a discrete value. Within that, it's somewhat linear. Okay, it's a probabilistic interpretation of this nonlinear layer, and it's a Gaussian interpretation of this nonlinear layer. Even this Gaussian interpretation is from a probability distribution, you can say. So both have some similarity, some resemblance, right? So now, how to choose gamma? Because if you have this topic is untouched, we have said that there is an impact of gamma in everything with such kind of a radial basis function. Now, how to choose a gamma where I know that my gamma is n equal to 1, or rather I would say now k equal to 1 to k wk e to the power minus gamma x minus mu k square. So now how I can choose this gamma? So that is the topic in next week lecture, which is called as EM algorithm. EM stands for expectation maximization algorithm. That I will choose gamma in order to maximize my expectation as mixture of Gaussians. So mixture of Gaussian is a model where you have seen this one. I have the final model as a mixture of all these Gaussians. So with respect to a weighted mixture, I am trying to get into a final model. So the final model should depend on gamma, as we have seen in that example, that in the mixture of this Gaussian model, gamma plays a significant role. So again, this problem, if we look, is NP-hard. So we solve this problem into step 1. As we will see in details, what I will do is that I will fix gamma and choose W1 to Wk, the k weights. Then for W1 to Wk, or choose is not a good word, I can say I can solve for the W1 to Wk. And for W1 to Wk, I will try to minimize error with respect to gamma. And I go on doing these two steps again and again until I converge. That's what I will do in this kind of an algorithm in the next week's class. But this is how iteratively we can converge and find the value of gamma. So now you may be tempted to think that why only one gamma for all the centers? It may be that I would like to have some set of points where my gamma diminishes like this, but some other set of points I want my gamma to be more flatter. And for some set of points, I want my gamma to be very steeper because I want a very less boundary influence. And here I want a medium range boundary. Here I want a very broader range boundary influence. Agreed, absolutely. I mean, absolutely granted. Then you have k parameters again, gamma 1 to gamma k, and you need to fix them, try to solve this one. Fix them means have some initial values and try to solve them with respect to that. Again, iterate over this, but all of them will be locally minimized, or we will get a local minima, but definitely this will converge as we have fixed set of points. As we have fixed set of points, so definitely this will converge with this radial basis function. Okay, the final word. So you already know that radial basis function is also can be applied in terms of kernel, right? I can also apply radial basis in terms of kernel. Obviously, you have seen in the last class that I can easily use this as a kernel.
Yes, sir.
Which, yeah, that's a common use, and radial basis function obviously have invented starting with this. Rather than people thought that Gaussian is a very good estimation of finding learning models with respect to Gaussian functions. So that we have already seen, and in case of SVM also you can use this one. Then your SVM equation will boil down to sign of finding sum of alpha n's greater than 0, that is your support vectors. Only the support vectors have alpha n greater than 0. This is your kernel part. Then you need to give x minus xn square plus this is your bias. So that is for your SVM. Isn't it look very similar to whatever we did in terms of classification, straight RBF classification? What we did in classification or clustering is k equal to 1 to k wk e to the power minus gamma x minus mu k square. We can add a bias in terms that we can just bias the points, I mean the classifier into, or the point distributions into a different, we can shift the distribution of the point. So you can add this and you can say otherwise the bias is 0, whatever you have got. So this also rings a bell that your SVM, the way you are classifying SVM and the way with this Gaussian RBF function, and the way you classify in terms of your from linear regression, you build up a model, has the similar kind of a nature. And though these two follows a different minimization or optimization criterion, as I have said, all these problems are NP hard. Therefore, this will give you some separation boundary like this, and this may give you not exact but a little bit different boundary between the points. That you may get it, because both of them has a different way of optimizing it. Though the optimization problem that they are solving is the same, but they have a different way of doing so. Finally, this is pretty interesting. RBF as regularizers. So see, what does regularization mean? If you try to recollect, regularization is nothing but making something a bit smoother. That's why second order polynomial sometimes is better than the fifth order polynomial. So I do not want to fit it like this, rather this is better for me. So regularization has an inherent property of finding smooth hypothesis, right? Finding smooth hypothesis that we have seen in different ways. What does smoothness means? Smoothness means with respect to, if you try to take the derivatives of the hypothesis with respect to the points, then your kth derivative your kth derivative with respect to the point, the more abrupt it is, the less smooth it is. Agreed with this philosophy? The more abrupt is your derivatives,
Agreed, sir.
less smooth is hx. Because your derivatives bring out the fluctuations in hx much more. The more bad is your derivatives, or more abrupt, more unsmooth is your derivative, the less smooth is your hypothesis will be. Hence, when you are trying to go for purely RBF into regularization aspect, what you do first, the fact that obviously I would like to minimize in regularization my error. That obviously is the case, that I will minimize my regularization. First of all, not in regularization, but generally I will minimize my error. With that, there is something, the regularization parameter, and what I would like to do, I will try to minimize this as well in order to bring smoothness in the curve. So it means that what I will do for kth derivative of this h function, I will try to make the error or the abruptness square dx, and then from minus infinity to plus infinity, I will do it with some ak as a parameter. So the whole role is that not to look at how this equation comes, because this is a very hairy mathematics. The whole role is that it is not about the minimizing the error only, which is obviously will get a good performing hypothesis. The second and more important aspect is to introduce smoothness. Now, if you calculate this as your error function and try to minimize the overall thing, it also minimizes the abruptness in your hypothesis as well as your error together. Then, depending on your regularization constant, that's your regularization constant, you will get a smoother hypothesis directly from RBF. Why? Because I cannot show the derivation, it's too much hairy. If you derive it, what you will get, your regularizer will be an RBF only. But it is not it is not difficult to figure out why it is an RBF, because obviously the influence be smooth if you take RBF as your hypothesis. So if you derive out this, which will minimize this thing, all the different kind of hairy mathematics if you put in, or any standard theoretical machine learning textbook, you will see that if you try to solve this equation with for minimizing the error, your hypothesis finally will come as an RBF. And it is not difficult to foresee that, because obviously this has a very smooth tendency function with respect to the points and its neighbors. So the function decays very smoothly, and therefore when you overlay this function in your hypothesis here to minimize the whole thing, your smoothness factor will automatically come inside your answer. So this we sometimes call the derivation and all that, fine, sometimes we call that smooth interpolation. Okay, so this summarizes the fact that RBF is a very generic model. We can use it in one side for regression from that classification, also the nearest neighbor method with a different basis function though. Then we can also move it towards clustering by having the distance of the similarity as you have taken as a cosine similarity, Euclidean distance, any kind of a distance matrix between the centers with respect to points. You can take this kind of a Gaussian or RBF functions as your distance matrix and can compute that. Finally, we have seen it forms a two-layer network, which is sometimes resembles with the neural network as well, because you need to learn the weights and the mu k's in two different layers, where the neural network learns it also. Then we have also seen traditionally it is mostly used in forming the kernels and SVMs, where you visit an infinite space as we have seen in the last class and come back with a value of e to the power that function. Also, the one of the great usage of it is that it's very smooth in terms of building your hypothesis, and it's a very good regularization function that you get out if you try to minimize such kind of formulation, and you will get finally you will end up with getting a RBF at the end. Okay, so with that, I would like to stop today's lecture. If you have questions, I can answer.
So this RBF is generic one, but which one to choose? This RBF or the our standard different algorithm for different problems?
No, you need to see. Now the thing is that you are only given with data points, right? So you need to switch between different algorithms, different models, and then try to find out that which is best through cross validation, generalization, and all that, right? So it depends on the data points and the distribution of data points that is given to you. RBF is a very strong model, but it is not widely or blindly used in any sort of data points, right? So you need to make yourself experimented with different sorts of models and corresponding algorithms to converge into the best one.
Okay.
Because you do not know the unknowns, the out of sample you do not know, right? So the in sample and the regularization are the two things that you have in your hand. Any other questions? Okay, so just one announcement before you leave. Let me stop the recording.